Let's discuss a common data question from GATE 2009. A common data question. So it's on radiation. So radiative heat transfer is intended between the inner surfaces of two very large isothermal parallel metal plates. Plate, which is plate 1, is a black surface and is the warmer one that is being maintained at 727 degrees Celsius. The lower plate, plate 2, is a diffuse and gray surface with an emissivity of 0.7 and is kept at 227 degrees Celsius. Assume that the surfaces are sufficiently large to form a two surface enclosure. So let's write down, assume that surfaces are sufficiently large, so basically it becomes a two enclosure and steady state conditions are reached. Stephen Boltzmann constant sigma is 5.67 into 10 power minus 8 watt per meter to the power of 2 by Kelvin to the power of 4. Okay, so first question is the irradiation in kilowatt per meter square for the upper plate is okay, and the options are given 2.5, 3.6, 17, D is 19.5. okay, and because it's a common data question, so the other bit is, so he now in the second question he says if the plate 1 is also diffuse and gray surface with emissivity 0.8, okay, the net radiation heat exchange in kilowatt per meter square between plate 1 and plate 2 is, so it is given as 17.0, 19.5, 23.0, D 31.7. okay, so there are two questions. Okay, so let's first do the first question. First you have, in the case, this is the question number 1, this is question number 2. So let's do question number 1. You have the upper plate being the black surface for the question number 1 and is warmer, so 727 degrees Celsius plus 273 makes 1000 Kelvin. okay, and the bottom plate, which is, this is plate number 1, or let me write plate 1, and this is plate 2, which is at 227 plus 273, it is 500 Kelvin. okay, now irradiation is the amount of radiation that is falling on it. Irradiation is the amount of radiation falling on the surface. So irradiation for the surface 1 is the black surface, and because the plates are very large, so the radiation that is coming from it is the radiation that is coming from plate 2. So basically the amount of radiation that is emitted by plate 2, all of that will fall on plate 1. So because it's a two surface enclosure, so the amount of radiation that is emitted by plate 2 is basically emissivity into sigma A T temperature to the power of 4. So this is your sigma A T power 4 is the black body emissive power into emissivity because it's a diffusive. So this is what is the amount of radiation that is emitted by surface 2. So let's calculate this. Emissivity for the plate is 0.7. Sigma Boltzmann constant 5.67 10 power minus 8. Area I don't need because it is asked per meter square. So area I'll just take to the left hand side. T to the power of 4, which is 500 to the power of 4. So this value, if I calculate, I get a value. So let's calculate this value. So this value, if I calculate, I get 2.48 kilowatt per meter square. And so this is close to 2.5 kilowatt per meter square. So it's fairly an easy problem. Answer for this is A for the first part. So just only tricky thing here is many of you may not know what is irradiation. Irradiation is the amount of radiation falling on the surface. I want amount of radiation that is falling on the first surface, and because it's a two-sided enclosure, so the amount of, and there's only two surfaces, so the amount of radiation that is emitted by surface 2 entirely falls on it. So amount of radiation emitted by surface 2 is emissivity into the black body emissive power, which is sigma A T power 4, and it's asked per meter square area, so I can just divide per meter square area, and the answer for this is A. Now let's solve problem number 2. So for the second question, it is asked that plate 1 is also diffused with emissivity of 0.8 and plate 2 is already has an emissivity of 0.7. So what is asked is the amount of radiative heat exchange between two. So when you have two surface enclosure, the amount of radiative heat transfer that takes place is sigma A T1 power 4 minus T2 power 4 by your, for the long plates it's 1 by epsilon 1 plus epsilon 2 minus 1. So this is the general formula which is derived. Okay, there's a derivation for it. So okay, so this basically, how do you obtain this? This is sigma A1 F12 T1 power 4 is the amount of radiation that emitted by first surface and that falls on the second surface, minus sigma minus the amount of radiation that is coming from the second surface. So if we subtract these two, this again the emissivities also have to be included. So considering all that, you get this general formula. Okay, so I'm just not deriving this because it is all derived in the books. This is for two very large plates, okay, with emissivities epsilon 1 and epsilon 2, then amount of radiation heat exchange is this. So as again we want per unit area, so area I bring it this side. So sigma is 5.67 10 power minus 8, temperature is 1000, so 1000 power 4 minus T2 is 500 power 4 by epsilon 1 is 0.8 is 0.7 minus 1. So when you solve this, you get a value which is closer to 31.36. so this is kilowatt per meter square when you solve. This is just you have to just use a calculator. So the answer for this is close to 31.7. answer is in kilowatt per meter square. So the answer for this is D. So only thing of interest here is to remember the formula, and this model is very important. Very two large plates, it's asked so many times. Okay, let's do a problem on GATE 2008 problem number. Okay, so this is again a problem on radiation. So a hollow enclosure, so let's write down a problem. A hollow enclosure is formed between two infinitely long concentric cylinders of radii 1 meter and 2 meters respectively. Radiative heat transfer, radiative heat exchange takes place between the inner surface of the large cylinder, which is surface 2, and the outer surface of cylinder, inner cylinder of the smaller cylinder, which is surface 1. And the surfaces are diffuse and the medium in the enclosure is non-participating. Okay, so what is asked is the fraction of the thermal radiation leaving the larger surface and striking itself is. Okay, so there are options for this: 0.25, 0.5, 0.75, 1, and there's a figure that is given. This is surface 1 and this is surface 2. Okay, so you have the larger surface, which is the surface 2, and what is asked is the amount of radiation leaving this larger surface and striking itself. Okay, so first let me tell you one thing. What is Fij? So this is important donation, is a view factor or the shape factor, which means the amount of radiation striking, amount of radiation leaving surface I. Let me write it clearly: leaving surface I and striking surface 2. So it's a fraction of the amount of radiation leaving surface I and striking surface J. Okay, so if the total is 1, then there might be 3 or 4 surfaces, so 1 might be participating with 2, 3, with 4 or 5. Okay, so that is F. So what we want is F22 is what is we want. Okay, so now first of all you have something called the summation rule for each surface. Summation rule. So for surface 1 it is F11 plus F12, that is sum of the radiation that is striking itself plus striking the second surface. There are only 2 surfaces, this has to be 1, and this can be written for surface 2 also. So for surface 2 it will become F22 plus F21, because some portion of the surface 2 that strikes can again strike it back, right? So this is also 1. Okay, and then there is, so this is summation, then there is reciprocity rule between any 2 surfaces. One can write surface area of it A1 F12 A2 F21. so this is for a pair of surfaces. So these are the 3 rules, and one thing is F11, that is the radiation that leaves surface 1 and strikes back, because it's a convex surface, so you can see, so you can't have a case where radiation that is leaving it can strike it, because whatever the radiation that leaves it can't strike it back. Okay, because it's a convex surface, it can't happen, right? Okay, it leaves like this, it can't strike back. Okay, so F11 is 0, so that is again clear. So when F11 is 0, from this equation I get F12 as 1, and I need F22, so I need F21, so I need to use here, so F12 is 1, so F21 would be A1 by A2. So A1 by A2 is the surface area, ratio of the surface area. So A1 surface area, this is pi d, pi into diameter into length, so pi d1 L and because it's infinite, so the length will cancel out. So A2 is pi d2l, so it's ratio of d1 by d2, which is nothing but r1 by r2, and that is nothing but 1 by 2. So f21 is 1 by 2, which I just substituted here, so I get f22 as 1 minus f21, which is 1 minus half, which is 0.5. so the answer for this is 50% of the thing strikes it back, so the answer for this is B. So these problems on shape factors, apply the summation rule, apply the reciprocity rule, most of the problems you can solve it. And then remember that if it's a flat surface or the convex surface, the shape factor with itself, that is f11, is 0. So all these problems you can solve in that way. Okay, so let's discuss question number 50 from GATE 2008 paper, question number 50. So for a three-dimensional object, for a 3D object shown below, 5 faces are insulated. The sixth face, PQRS, which is not insulated, that's thermally with the ambient with a convective heat transfer coefficient of 10 watt per meter square Kelvin. Okay, the ambient temperature is 30 degrees Celsius and heat is uniformly generated inside the object at the rate of 100 watt per meter cube. Assuming the phase PQRS to be at uniform temperature, its steady state temperature is okay, so you have a, let us draw the figure. Okay, so this is PQ. Okay, there is a dotted. Okay, so this is R on the back side, this is S, this is H, this is G, this is F, this is E. Okay, so this is 2 meters and this is 1 meter, and this is again 2 meters. Okay, and the options are 10 degrees Celsius, 20 degrees Celsius, 30 degrees Celsius, 40 degrees Celsius. Okay, so for a 3D object, let's read the question again. 5 faces are insulated. Sixth face which is not insulated. PQRS is something which is not insulated. That means it can lose heat or gain heat. And this is the surface that interacts thermally with the convective heat transfer coefficient H of, so H is 10 watt per meter square. So only this surface PQRS can share heat. The ambient is 30 T ambient and H is also given, and object is generating heat. Assuming the phase to be at a uniform temperature, its steady state temperature. Okay, so when this object will reach steady state? Okay, now heat is generating uniformly, heat is getting generated uniformly. So if it doesn't lose any heat, obviously the internal energy of it will increase and the temperature will rise. But then for it to lose steady state, the amount of heat that is built up, the rate at which heat is getting built up inside should be the rate at which it loses heat, and the only phase where it can lose heat is PQRS. So the heat is getting generated uniformly. Okay, so for steady state, heat generation rate should be equal to the heat lost or rate or heat dissipated rate. Okay, and that is by PQRS surface through convection, because that's the only way it can lose heat. Okay, so heat generation is given as 100 watt per meter cube, so that is 100 watt into the total volume is the heat generation rate, and heat lost is HA, the temperature of the PQRS steady state minus the ambient temperature. So this is what we want. So 100 into volume is basically it's a cuboid, so LBH, length, breadth into height, so that is the volume. Heat transfer coefficient is given as 10. Area, okay, so this area is the area from where it is losing the convective heat, so that is nothing but PQRS, which is nothing but 2 by 2 QRS. PS is 2, RS is 2, and temperature is what we want. T infinite is 30. So this is 100 into 4 by 10 into 4 is T minus 30. So this you get 10 is T minus 30. So T is 30 plus 10, that is 40. The answer for this is D. So this is again a fairly energy balance problem. You have to just understand what is happening. Let's discuss GATE 2008 question 45. The logarithmic mean temperature difference, that is the LMTD of a counter flow heat exchanger, is 20 degrees Celsius. The cold fluid enters at 20 degrees Celsius and the hot fluid enters at 100 degrees Celsius. The mass flow rate of the cold fluid is twice the mass flow rate of the hot fluid. I am just writing in the mathematical form, and the specific heat for the hot fluid is twice the specific heat of the cold fluid. The exit temperature of the cold fluid is, so this is 40 degrees Celsius, 60 degrees Celsius, 80 degrees Celsius. T cannot be determined. Okay, so now let's draw counterflow heat exchanger. So the hot fluid enters at 100 and I don't know when it leaves, so this is 100. The cold fluid enters at 20 and I don't know where, what temperature it leaves. So this is THI TCO, this is THO TCI. So this is a counterflow heat exchanger. Hot, cold, temperatures versus the length. Okay, so now when I do just the energy balance, what I get is MC for the hot, MC hot is THI minus THO. The heat lost by the hot fluid is the heat gained by the cold fluid, CC by TCO minus TCI. So mass of the hot cold is twice the hot, but the specific heat of the hot is twice. So this factors, these two will become equal, right? Because mass of the cold is twice mass of the hot, and mass and specific heat is twice mass of the cold, right? Mass of the cold, CPC. So these two basically becomes equal. I mean, so what these two factors will become equal. So finally what we get is THI minus THO is TCO minus TCI. And so here Thi minus Tco is delta T1, so that is Thi minus Tco. So Thi minus Tco from this, if I bring this side and this that side, so Tho minus Tci. And what is delta T2? Delta T2 is Tho minus Tci. So what it means is basically delta T1 is equal to delta T2. And when you are writing LMTD, the basic formula is delta T1, the temperature difference on one side minus temperature difference on the other side, by Ln delta T1 by delta T2. So when delta T1 is equal to delta T2, which is the ideal, which is the very rare case, and that's what happened in this problem. So when these are equal, you may think that this denominator blows up and Ln it becomes zeros. No, that's not the case. So when delta T1 is when delta T1 is equal to delta T2, see, remember this formula is derived. When you derive this formula, there's a basic one important step where you make an assumption that delta T1 is not equal to delta T2 and derive this. So when delta T1 is equal to delta T2, the LMTD is just equal to delta T, and which is nothing but delta T1 or delta T2, because both are equal. So under the case when delta T1 is equal to delta T2, LMTD is just the delta T. Okay, so in that case my LMTD is just the delta T1 or delta T2. I need the cold temperature at the exit temperature of the cold fluid, so let's use that the LMTD is delta T1. So LMTD is 20, delta T is Thi minus Tco. Thi is 100 minus Tco, which is what I need. So Tco from this is 100 minus 20, which is 80. So the answer for this is C. So only important thing what you have to understand is when the delta T1 is equal to delta T2, that is the temperature difference on one side is equal to the temperature difference on the other side, the LMTD doesn't mean infinite. It means that, see, remember this formula has to be used when delta T1 is not equal to delta T2, and when delta T1 is equal to delta T2, LMTD becomes basically the delta T, either of, delta T, which is nothing but delta T1 delta T, and that formula you have to use to determine. So this is an important problem. Thank you.